We'll continue our discussion on support vector machines. So in support vector machines, we have looked at a few topics. The first, we discussed that it's a binary classifier. We then said that the objective is to maximize the margin, but we said that just maximizing the margin does not work. We also have to additionally do what? Ensure what? So in the objective, we mentioned that we have to maximize the margin. In addition, what else do we need to take care of? Yes, in addition, what do we need to do? You have to ensure that each of the point is on the correct side of the margin. So which are the inequality constraints? So we first looked at that formulation. We said that that particular formulation is a quadratic program. So if we go over the slides. Right, we said it's a binary classification technique. We want to maximize the margin. The points lying on the margin are called support vectors. We also said that we also derived the equation of a hyperplane w dot x plus b equal to 0. We found the distance between two parallel hyperplanes. And then we finally came to this formulation that we have to maximize the margin, which is equivalent to minimize w vector's magnitude, subject to correctly labeling all the points, which are these inequality constraints. So therefore, we have the original formulation in the primal form, which is minimize half magnitude of w squared subject to the linear inequality constraints. This is a quadratic program. We looked at an example in 1D where we geometrically looked at the inequalities and found that in this case 2 out of the 4 inequalities were binding in nature. So they decided the overall feasible region, and minimizing the w over that feasible region gave us the w for this SVM problem. So we also said that the constraints which are binding in nature, only they will correspond to the support vectors. All the other constraints do not correspond to support vectors. We then looked at the dual formulation, which introduces 1 alpha per inequality, and it gives us the minimization of w in the primal is equivalent to maximization of this function of L of alpha. The constraints are now different. Previously we had constraints, just inequality constraints. Now we have inequality constraints as well as the equality constraints. For what kind of points are alpha is equal to 0? Support vectors or non-support vectors? Non-support vectors alpha e is equal to 0. For support vectors alpha e is greater than 0. And we also said alpha I yi summation over all the n examples, n inequalities has to be 0. We then looked at the same example from the dual perspective, and we also showed how we can calculate b from the dual perspective. We then said that in the dual, if we have to make any prediction, it's the sign of summation I equal to 1 to number of support vectors alpha I yi xi dot x test plus b. So therefore, what we are saying is that when we want to make a prediction for any given test point, we calculate its dot product with all the support vector inputs, and there is a multiplier corresponding to alpha I yi, and then there is an intercept or bias term that you add. We then looked at the fact that data can often not be linearly separable. So we said that maybe we should project the data to high dimensional space via basis function phi, and in that function, in that projected space, the data should be linearly separable. So what we said is, like in this case, we have a basis function or a function which expands the dimension as root 2x x square, and after that we can observe that the data is linearly separable. But we said that we can, so then the only thing which needs to change in the dual formulation is that instead of xi dot xj in L of alpha, we now write phi of xi dot phi of xi, phi of xj. So wherever we have xi vectors, we replace them with phi of xi. But we said that there is some problem in this approach, which is that phi, firstly the projection step is expensive, secondly the dot products in the high dimensional space is also very expensive. So instead what we said is we want to use the kernel trick, which is to say that we have a function k of xi dot xj, which gives you a notion of similarity between xi and xj. Second, it is involving dot products in the low dimensional space, in the original space. And third, importantly, this is equivalent to the dot products in the high dimensional space. We looked at the kernel trick, we looked at the transformation that it is producing, but importantly we said that we are using the dual form because it enables us to leverage the power of kernels. In the primal we don't have phi of xi dot phi of xj form. In the dual we have that, and we can replace phi of xi dot phi of xj with k of xi comma xj. We looked at a few kernels. In this linear kernel we can very easily see that it involves dot products in the original dimension. Polynomial also we can see xi dot x2, x1 dot x2 vector. In Gaussian or the radial basis function we don't directly see it here, but when we did a bit of expansion we can see that we will still get terms which involve the dot product of the two vectors. And we said that the RBF kernel lies in infinite dimension space, so you cannot even solve it by projecting the data to a high dimension. We then also looked at the interpretation of RBF. We looked at a specific notebook where we said that if our x support vector or any fixed reference point is 1, and then we compute the kernel evaluation for x comma x support vector where x is varying from -5 to 5. So this is the kernel functional evaluation that you will get. For x equal to 0, you will get always a 0 because 0 vector multiplied with any other vector will give you a 0 vector, or dot product with that will give you 0 vector. Importantly, we looked at the Gaussian kernel with varying degrees of gamma. So Gaussian kernel is telling you now how similar is x equal to 2 with respect to x equal to 1. So therefore, so do you expect x equal to 2 to be similar to x equal to 1, or x equal to 3 to be more similar to x equal to 1? X equal to 2, right? So therefore you can see the kernel function at x equal to 2 comma, so k of x2 comma 1 is much higher than k of 3 comma 1. So therefore it is incorporating the notion of similarity. But when you are varying the gamma, the similarity or the kernel function dies off or becomes flat at varying rates. At low gamma, we can see that the kernel function is very flat, whereas with high gamma we can see that the kernel function drops off very quickly. So what we can understand with high gamma is that any point has very limited influence on the other data points. So when we make a prediction, when we made the prediction, we had this particular equation where I had x test. I don't know where that equation went. Right, this equation. So what we're saying is that this xi dot x test or phi of xi dot phi of x test you will replace with the kernel functional evaluation. That is this thing we have been repeating. Now if the kernel functional evaluation, if gamma is very high, then the kernel functional evaluation would be dropping off to 0 very quickly, and only for a very small number of values in the vicinity of this support vector on the vicinity of x test you will have certain high values, otherwise it will have 0 values. So what that is saying is that the impact of any point when gamma is very high is over a very small subspace. As you increase gamma, each point has very limited influence on faraway points. It has a very local influence. We also saw this via the covariance matrices that we had drawn. As you increase gamma, you can see that the relationships between points become 0 very quickly, whereas if gamma is low, then the points are related even if they are far. So x equal to 0 and x equal to minus 2, x1 equal to 0 and x2 equal to minus 2 still have some non-zero correlation, covariance, whereas if we look at x equal to 0 and x equal to minus 2, when gamma is high, the value is 0. So all of them are different ways of understanding the same thing. And then let me just go and discuss the different kernels for a given data set. So if this is the data set, you can very clearly see that it is not linearly separable. So therefore we need to project it to some high dimensional space. If we used a linear kernel, you'll get poor accuracy as expected on the training data set. If you get poor accuracy in the training data set, what problem do you call? High bias or underfitting. Have we circulated the tendon sheet? Okay. So that problem is known as high bias. We can clearly see that the train accuracy is very poor. So then perhaps what we'll suggest is that maybe project the data to a high dimensional space. Instead of the linear, let's use the polynomial kernel. So now immediately can you see that with the polynomial kernel, the train accuracy has gone from 0.59 to 0.78. And this is a degree 2 fit that we have done. Now we finally use the RBF kernel, and this is the fit that you get. So here can you see that the RBF kernel fit seems fairly similar to polynomial fit. Why is that? What was the formula for the kernel? If you expand the formulation for the kernel, did we discuss that it can be seen as sum of polynomials of different degrees? So therefore this seems correct. But now I want you to tell me what happens. So in this case, gamma is very close to 0. If gamma is very close to 0, then what can you say about the covariance matrix? Can you draw that? You should remember it by now. How would the covariance matrix look like for a very small value of gamma? So covariance matrix computes the k of x comma y for x varying from, let's say, -4 to 4 and y also varying from -4 to 4. It's a square matrix. Obviously at the diagonals you will get 1 values. So you have to tell me how the covariance drops as you move away from the diagonals. It would be good exercise to draw this on your notebook. That will also tell you how attentive you've been in the lecture. Okay, have you been able to draw the function? Now on the right side of whatever you've drawn, can you draw it for a larger gamma value? So I just want you to show the comparison between these two, for a low gamma and for a high gamma. If you understand this, you should be able to also understand the next things that we'll discuss. Okay, have you been able to draw those things? So these are now similar to the notebook which I had shown just a few minutes back. You should see something like this. With low gamma values, the influence of one point extends to a very large distance, whereas with very high gamma, the influence of one point is very narrow. So high gamma means more local, low gamma means more global. Right? So as you increase gamma, your influence becomes more and more localized. Okay, so now if you look at this plot, can you see that the training accuracy is 0.73, not very good, and can you also see that there are a lot of misclassifications. For example, this particular point is predicted to be the blue class. Now can anyone tell me why is this predicted to be the blue class? Right, it lies outside the margin, that is from the, like once you've drawn this you can tell that, but can you see that it is surrounded by a lot of blue points? Now if you were to look at the influence of the other blue points, it will likely overpower this specific point, right? So therefore what we are saying is that for very low gamma value, the influence of points is very large. So therefore this brown point is affected by this blue point, this blue point, this blue point, this blue point, so on and so forth. Actually it's affected only by the support vectors, but just for the simple purposes of illustration. Now can you tell me what happens if I increase gamma? What will happen if I increase gamma in this plot? There are a few numbers here. One is the train accuracy, one is the plot itself. One is support vectors also, but for now let's ignore the number of support vectors. How would you expect the train accuracy to change if I increase gamma? Okay, first column, orange t-shirt. If gamma increases, what happens to the train accuracy and why? Any guesses? It will either increase or decrease. You only have two options. Okay, Ishwar, what do you think? Decrease? Why do you think it will decrease? Okay, Rajat, what do you think? Why do you think it will increase? Because I didn't give a very positive response to the previous question. Why will it increase? Okay, so let me ask a simpler question. If the training accuracy has to increase, how would, so let's just focus on this point. If the training accuracy has to increase, should this brown point be predicted to be the brown class? If this brown point has to be predicted to be the brown class, how would the contours look like? Will they be this contour only or will they change? They will change, and that is where you get the answer. So this is with respect to gamma equal to 0.01, it almost looks like a linear SVM, very poor. The train accuracy is 0.61. Now if I increase it to 0.06, you can now see pretty much equivalent to the polynomial kernel, looks very similar to the polynomial kernel. Now I'll just play through this animation and then we'll come back and discuss more details. So just focus on this brown point only. As of now, the training accuracy is increased significantly, but this brown point is still predicted to be the blue class. What is the this particular brown point now predicted as? The brown class. What is happening? Can someone now tell me? As I'm increasing gamma, what is happening over the influence region of a particular point? So talk in terms of local versus global. As gamma increases, the influence becomes more local, right? So you can see that there is very limited influence that one point has on the vicinity, which you could also understand from this kernel, from this covariance matrix. If you had one point, let's say, and this is just 1D points, but you can have the same in any dimensional points. As you're increasing gamma, the influence becomes very local, so therefore only the values which are very close to you would be predicted to be that class. And if I keep increasing gamma, just keep observing how the contours will behave like. Maybe let's look at any other point which is being mispredicted as of now. So maybe let's look at this point. This blue point is currently mispredicted. Okay, is this blue point now correctly predicted? Again, because this blue point should is very close to the other brown points, so you'd probably think it to be predicted to be the brown class, but because the influence has now become very local as the gamma value has increased to a huge value, so therefore it is only looking at the vicinity now. Let's keep going further. Now maybe this brown point. The points which are marked with the black borders are the support vectors. So you can also see how different points start becoming support vectors. This brown point is what we're focusing on. Currently it's predicted to be the blue class, and this one would be very hard to get correct because above this is blue, below this is also blue. Only to the right hand side there is one brown point, and this itself is a brown point. You can also keep a note on the train accuracy. The train accuracy is increasing. The number of support vectors also seems to be increasing. So now this brown point has been accumulated in this brown set of points. We keep increasing further. This blue point is currently predicted to be brown class. This will also develop a region on its own, some island on its own, where it will be predicted to be the blue class. Beyond this point it's not changing much, but let's say if we directly go to a much higher value. Right, so now the training accuracy is 98%. You can see a lot of these local islands of points which seem to be anomalous. So now is your classifier underfitting or overfitting? Overfitting, because if you were to change even one point, it will exhibit a high amount of variance. Your entire model's prediction will change. So therefore, in terms of bias variance trade-off, very low value of gamma, high bias, very high value of gamma, high variance. So therefore, in any machine learning, in most machine learning models, you should be able to study the bias variance trade-off. Here it's very easy to understand in terms of the locality. As you increase gamma, the locality increases, therefore you will be only looking at very local regions, you will not be looking at global trends. Now very high gamma value, let's try and correlate it to what happens in k nearest neighbor. Does high gamma equate or become very similar to low k or high k in k nearest neighbor? How many say high gamma is similar to high k? How many say high gamma is similar to low k? So I think you've got the concept. So this is where I think, as I mentioned earlier also, generally when we talk about various hyperparameters, generally across many classifiers models, increasing the hyperparameter increases the variance. K nearest neighbor is an exception because k equal to 1 refers to more locality. Now you can also think of this as just k nearest neighbors, very similar to k nearest neighbors with k equal to 1, and then you'll start getting a lot of locality. K equal to 1 might be even more local in nature, but you broadly get the concept. Okay, any questions on this? Okay. So then we'll go on to the other method of handling non-linearly separable data, which is via something known as the soft margin. So this data is slightly non-separable. So what we're saying is that maybe there is just this one blue point and this one red point which are violating the boundary, which are violating the separating hyperplane, but more or less it looks correct. If we chose this line, these 2 points could also have been anomalous, they could have been some issues with the data set. So therefore what we want to say is that maybe we should be okay with tolerating a little bit of such points. We may not be able to linearly classify the data. In this case, if you want to do a previous linear SVM, you can't learn that, because this red point and this blue point are very close to each other. You won't be able to learn a boundary. So we don't want to project the data to high dimension, that we have already seen in the case of kernels. We want to instead introduce some slack, typically denoted by psi of I or epsilon of I. We want to say that some samples we are okay with being misclassified in the training data set. So that is an important consideration. This psi is the loss or penalty that we put on the samples which are going to be misclassified. So the loss or penalty you put on samples which are going to be misclassified, which means that if a point is correctly classified, what is the value of psi I? This is the loss or the penalty you put on points which are misclassified. If the points are correctly classified, what value of psi I do you want to give? 0. So we also then write the misclassification as the distance from the margin. So for example, we will say that this particular point is on the correct side of the hyperplane but on the wrong side of the margin. This red point is on the wrong side of the separating hyperplane itself. This blue point is also on the wrong side of the separating hyperplane itself. So we call this as epsilon I, the distance from the corresponding class margin.
Sir, why do we give it to be 0, why not infinite?
Why do we give it to be?
You just mentioned that if we want perfect classification, we take the slack to be 0. Shouldn't it be infinite?
We take the slack to be 0. I mean, there is, so in this formulation, if you look at epsilon I, so epsilon I is the distance from the margin. So for example, for this particular red point, would you call the distance, would you put a negative penalty? No, there is no notion of negative penalty. On the points lying on the support vector, again, you don't need to put any penalty. So we're just talking about epsilon I as the deviation on the other side of the margin. We'll come on to a specific question in about 10 minutes about infinity. So we'll come on to that. So the here epsilon I is the distance from the margin. Now we have 4 different zones where the points will lie. The first zone is where yi equal to +1 and w dot xi plus b is greater than equal to 1. So maybe this red region. For this blue region also we'll have the same zone effectively, because yi into wxi plus b is greater than equal to 1. There is no loss for all the points lying in this region. So therefore epsilon I is 0, no penalty or no slack needed. These are the points which are correctly classified. The second zone is the points lying on the margins. So on the margins we know that wxi plus b into yi, that will be equal to 1. So therefore on such points also there is no deviation from the margin. So therefore we say that their loss or their epsilon slack is also 0. Zone 3 is where yi into wxi plus b is less than 1. So first for simplicity, just consider the red points. So yi is +1 for the red points, and the separating hyperplane is wx plus b equal to 0. The margin is wx plus b equal to 1. If yi is 1 and wxi plus b for such points, do you see it will be a number between 0 and 1? This corresponds, this line separating hyperplane corresponds to wx plus b equal to 0. The margin corresponds to wx plus b equal to 1, and for yi equal to 1 we don't look at the sign. So therefore we can say that all the points lying on the correct side of the hyperplane but on the wrong side of the margin, they will have a loss not equal to 0, but the loss will be between 0 and 1. So these points are correctly classified but on the wrong side of the margin. And zone 4 are the, so we can also write the equation of this particular line where this point is lying as wx plus b equal to 1 minus epsilon I. Points lying on this line, their y value corresponds to, sorry, their plane value corresponds to wx plus b equal to 1 minus epsilon I. Zone 4, again we are talking with respect to the red class. are the sets of points which are incorrectly classified and they're clearly on the other side of the margin. They have to be. So for such points, we can see that yi was plus 1, wx plus b has to be less than 0 now, because this separating hyperplane is wx plus b equal to 0. So therefore, for such points wx plus b is less than 0. So therefore, yi was positive. So therefore, we can say that yi into wx plus b is not equal to 1, it's less than 1, and the epsilon I has to be greater than 1 for such cases. For the points lying on the separating hyperplane, the epsilon I equal to 1. For points which are even further away, epsilon I is greater than 1. You can similarly derive for the blue class points, but talking in terms of the red class is slightly easier because yi you don't need to factor, that's plus 1. And the equation still remains wx plus b equal to 1 minus epsilon I, where epsilon I is now greater than 1. So we will now change the objective. The previous objective was half w squared or half the norm of w squared subject to yi wxi plus b is greater than or equal to 1. We introduce the slack variable. We introduce a multiplier for the overall slack, that is c times summation I equal to 1 to n epsilon I, subject to yi wxi plus b is greater than or equal to 1 minus epsilon I. Now the important thing to consider here is that for points which are on the correct side of the margin, what is the value of epsilon I? 0. So for such points we can notice that the slack does not take part, and here also we have the original conditions, yi wxi plus b is greater than or equal to 1. For points on the margin, on the other side of the margin, you will see how this slightly varies. And once you have written the primal, we can also write the dual form. Minimize summation alpha I and then I equal to 1 to n and j equal to 1 to n. This is the double for loop, or the yi yj xi dot xj, or which you can then replace with the kernel. Importantly, previously we knew that alpha I is greater than or equal to 0. Now we will write alpha I is between 0 and c, where c has to be a non-negative number. And the other condition remains as it is, summation alpha yi equal to 0. So we can now look at the bias variance trade-off with respect to C, and I want you to draw that. If this is a given data set and this is the objective given to you, half w squared plus c times summation I equal to 1 to n epsilon I, can you draw what happens, what is the margin when c is a small number and c is a very large number? Can you do that in your notebooks? Can you repeat your question? Dual is maximization, this is a typo. So you have to draw this simple figure, and then, so maybe first draw this in your notebook, and then I will take you back to the previous equation. Okay, if you've drawn this data set, now go back to the primal form only, forget about the dual. Look at what happens when c tends to 0 and what happens when c tends to infinity. One is you could mathematically try and solve it. The other is you could think of what the role c is playing and why we were introducing slack variables. One of these cases is hard margin SVM, or the SVM which we studied when we first started discussing SVMs, where we do not have any slack. And we do not have any slack means we are not allowing any misclassification. So you have to figure that out also. Do discuss with the neighbors. Don't just sit idle if you are unable to figure out a solution. Was that an alarm or a phone? Okay, does anyone want to volunteer and tell me what the plot will look like for low value of C? If you don't volunteer, you face the risk of me waking you up. And you'll have to be louder.
Separating hyperplane in the between and the
It will be between, but between what?
in the middle point.
Okay, so tell me, is the separating hyperplane where my cursor currently is, or here? This one? Do people agree? Is this where the separating hyperplane would be? Or no? Anyone else wants to volunteer? It will be between the two blue points. Okay. So Shitakshi says that this is where the separating hyperplane should be. Why do you say that? You're on the right track. Okay, good. C is 0, close to 0, which means that you don't mind having slack. Right? This term can be any large quantity, but because it's multiplied with a very small quantity, you don't really care that much. The objective is not changing that much. Or C close to 0 just means that you are allowing as much slack as you want. So if you want to allow as much slack, you will maybe have the line over here. So I redrew, sorry, just to make things slightly visually better. Wx plus b equal to 0. If I choose this particular line, can you see that the margin is very large? It's probably as big as it can get. We don't mind the violations. That is why small c value ensures that we don't mind the violations. Low c means low penalty for violations, which means that you will get high training error because you can misclassify certain points, which also means you'll have high bias. On the other hand, if c is very large, what it means is that you care a lot about misclassifications. You don't want any point to be misclassified, and which means that if it's a fight between maximizing the margin, so the first term is maximizing the margin, the second term is trying to minimize the violations. The minimization of the violations is going to win, which means that the margins will have to be shrunk down. And if the margins are made smaller, then we see that if the C is very high, there is a very high penalty for violation, and there is very high amount of variance, and the margin is very small. So high variance, small margin go together. Any questions on this? Okay, so if we go back to this formulation, okay, so what you're saying is that if C, firstly we'll never put exactly 0, we'll put a very small number, right? If C is a very small number, then what happens? Okay, so if C tends to 0, you're saying that alpha I will also have to be a very small number. Yeah. So if we look at it here, which is true. So alpha I will indeed have to be small if we look at this value. So let's do one thing. I will show the notebook in a few minutes. We'll vary C, and we'll also see what happens to the number of support vectors. How many alpha i's are exactly 0 and how many alpha i's are non-zero. So one potential effect could be that, and I'm just hypothesizing, that maybe the number of support vectors will increase and their individual alpha values will be smaller. But we'll see in the notebook. But if we just look at from the primal perspective, sometimes the dual can be a little hard to interpret because of the coefficients like the magnitudes, etc. But in the primal, in this specific case, that's how we derived this primal, that any violation means that we will not be particularly bothered about the violation. Which also brings us to the other question. So I said that, by the way, C tends to infinity, very large. The objective is just minimizing. You'll have a small margin, but you'll have any violation, which is also known as the hard margin classifier, no misclassification. Now we'll also look at what constitutes a support vector in soft margin SVM. In hard margin SVM, the definition was easy. The points lying on the margins are our support vectors. But now you're looking at the points lying on the margin as the support vectors, points lying on the correct side of the hyperplane, but separating hyperplane, but on the wrong side of the margin, they are also called support vectors because they are also influencing your overall decision making. And the points which are on the wrong side of the margin of separating hyperplane, they are also called support vectors. So therefore we have 3 zones of support vectors. As C increases, okay, I have written this down also. As C increases, the number of support vectors will decrease, which also answers your question. If C is becoming smaller, then we will likely have more number of support vectors, which might also mean that, so okay, so in this case, what do you think is the number of support vectors? 1 or 6 or 7? So look at the definition of support vectors. Let's first see. The first category of support vectors are which are on the zone 3 or zone 4 here, which are correctly classified but on the wrong side of the margin. The second are misclassified. So is this point on the wrong side of the separating hyperplane? So this is a support vector. But what are the margins? What is the margin in this case? Will the margin be along this blue line and along this red line? Can we see that? Right. So that's where the margin will be. You are trying to maximize the margin, right? So the margin has to be where the closest points are, except for the violation. So the margin lies on these 3 blue points and these 3 red points. So each and every point is in some sense acting as a margin. And you're correspondingly also seeing that the alpha values are small. Whereas in this case, what is the number of support vectors? You look at the margin, which is the closest set of points. You have 1 blue point and 3 red points. So therefore the number of support vectors is 4. So therefore what we're saying is that as the C value increases, the number of support vectors will decrease. Because now your support vectors will not, there will be no support vectors lying in zone 3 and zone 4. We can also look at this notebook first to understand a little bit more. Okay, non-linearly separable data. I am using a linear kernel and I am varying the C value from 0.0001 to all the way till almost infinity, 10,000. And I am fitting this linear kernel with the different C values, and I am just doing some regular plots. So C is very small. The number of support vectors is 100. Can you see? So here I am marking the support vector with a small black dot. The number of points in my data set was 100. If C is very small, each and every point is acting like a support vector. Right. So as per the definition of in the dual, we said that a support vector has non-zero values of alpha. Right. You have said all the values of alpha are between 0 and let's say 0.0001. So if we were to actually look at the dual coefficients, you will see many of them are very small, right, but a large number of them are very small. Just one second, let me just let me first just plot the first one. If we just plot the first one, and what is the method called? CLF. Was this is the same as the value that we have given, as the C value that we have given. So all of them have to be greater than 0 because all of them end up being support vectors. In this case, they are just values of the same values as pluses and minus. Actually, it's like this, it should be like this. All of them are the exact same value. Instead, if we looked at all these values, let me plot for the first two. Now this is the second case when C is equal to 0.001. Again, the number of support vectors is 100. It will be interesting to now see if all the values are same or not. Seems to be the same. When all the points are there as support vectors, it's turning out that their contributions, individual contributions are the same. Their alpha multipliers are the same. For the next one, I would definitely hope that we don't see each and every point as a support vector. Now the number of support vectors is 41 because there are 59 points which are now on the correct side of the margin, so they're not acting as support vectors. So again, you can clearly see that these red point where my cursor is, these are on the correct side of the margin, correctly classified, but on the wrong side of the separating hyperplane, whereas this red point, this red point, this red point are on the wrong side of the separating hyperplane itself. So by definition, all of these are support vectors. As C has increased, the number of support vectors has decreased, and now if you look at the dual coefficients or the alpha values, they will likely be not the same value. Right? At least two of them are not the same value. Here actually I think if we add these two, so if we don't look at the absolute value, they both should be from the same class, I would expect, because they need to be added to get u 0.1 or minus 0.1. But if we increase C further, and now let me just do it over all the points. Now C was 0.1, C is 1, the number of support vectors is further reducing. C is 100, number of support vectors is 35, C is 10,000, the number of support vectors is 35. For this data set, will we be able to get the equivalent of a hard margin? If I keep C to be a much larger number, I said C tending to infinity means the hard margin SVM. Will I be able to learn something here if I increase C beyond a limit? Let me repeat the question again. If C is, I set it to infinity. We technically can't do that, but let's assume it's a much larger number. What do you expect in the optimization? Because the data is clearly not linearly separable. So So one, you will see that the amount of time which it is required will be very large. Okay, sorry, I should have done. It's taking a long time because it's trying to compute an optimization which is not feasible. Right? You won't be able to ever find a hard margin in this example because the data is clearly not linearly separable. It will try its best. I don't know what it will eventually give. Let's come back to this when this finishes. In the meantime, let's continue with the slides. The margin will decrease as C increases, but here you will not be able to find a margin because C is so large, C is almost tending to infinity and the data is not linearly separable, so you can't do anything now. So typically in practice when people use SVMs, they use a combination of the soft margin SVM as well as the kernel functions. Okay, the margin is extremely narrow, you can notice it. The support vectors has definitely increased, but it's a very bad class. It's an okay classification actually, but the margin is so thin that it will exhibit a huge amount of variance. Just one second, let me get rid of this.
In that case, we saw yellow points on both the sides being zero.
Just one second, let me. Is it getting updated? Yes, okay. Oh, you wanted to see that?
No, I'll tell you my observation. Yellow points on both the sides were the support vector. But
Yellow
it was very small, so one
Yes.
side should be correct, one side should be wrong.
Okay, I didn't notice that. Let me run that again. We'll come to it. But in the meantime, let's. Now the most interesting aspect of this particular form is that we can now write it in a way which is very convenient to use your regular solvers like gradient descent like methods. So we have the objective as minimizing half second L2 norm squared of W plus C times I equal to 1 to n summation epsilon I, and we know this that yi wxi plus b is equal to 1 minus epsilon I, or epsilon I you can rewrite it as 1 minus yi into wxi plus b. Now we know that epsilon I is greater than or equal to 0. So therefore if we rewrite, we can write epsilon I to be the max of 0 comma 1 minus yi wxi plus b. Now does this remind you of anything you have seen earlier? What function? The ReLU function, but in a slightly different fashion it's occurring, but it's the ReLU function only. So therefore now you have written epsilon I in this particular form. Now if we rewrite the objective, we can write it as minimizing C times summation epsilon I just bring this to the left, plus half the magnitude of W squared, which is minimizing C times, I just now replace epsilon I with this definition, max of 0 comma 1 minus yi wxi plus b plus half W squared. We just bring the C back on the other side. So therefore we write minimizing this function, which is the loss function, plus 1 by 2c times W magnitude squared, L2 norm squared. Now does this look very similar to ridge regression to you? The first is the loss function, there the loss was the squared loss, here the loss is known as the hinge loss. It's a hinge loss because the loss we'll see, let me. Does this look like the way you open or close a door, the hinge of a door? So therefore this loss is known as the hinge loss, or if you are thinking in the correct terms, you could also think of how ReLU is being used and how it's similar. So you have the first component which is minimizing a loss in terms which is having parameters W and B plus the regularization term which just contains W. So now you have been able to conveniently write the SVM formulation with the soft margin SVM in the loss plus penalty form, and this is the loss function you can see for varying values of yi into wxi plus b. If yi into wx plus b is a number greater than 1, so therefore you put 0 loss. So you can think of what is, okay, I have those examples also. What corresponds to wi into yi into wx plus b equal to 0, so equal to 1? What are those points called where yi into wx plus b is equal to 1? Are these points lying on the margin, right, for which you have yi into wx plus b equal to 1? So for such points, we said that we should not be putting any loss, right? They are on the margin. Let me pick up. Okay, Bhaumik, for yi into wxi plus b greater than 1 from this diagram, greater than 1, so it is this region where my cursor currently is, there is 0 loss. Can you explain why? Yeah, that's a mathematical formulation, but conceptually, when yi into wxi plus b is greater than 1, why should be there? Why should it have 0 loss? What can you say about the points where yi into wxi plus b is greater than 1? Are these the points which belong to zone 1, where yi into wx plus b is greater than or equal to 1? For such points, we said there should be no loss, there should be no slack required. So therefore, we can see that yi into wxi plus b is greater than 1. When it is greater than 1, there is 0 loss. So the y-axis is a loss, sorry, I didn't label it. At yi into wxi plus b equal to 1, again 0 loss. These points correspond to the support vectors or the points lying on the margin. For all the other values where yi into wxi plus b is less than 1, they will introduce a loss as per this definition. So zone 1, zone 2, yi into wxi plus b is greater than or equal to 1. So therefore, we don't need to put any penalty on them. Zone 3, we need to put a penalty equivalent to the distance they are from the margin. Zone 4, again we need to put a penalty corresponding to the distance they are from the margin. And that is exactly what is happening in this hinge loss plot. So when yi into wxi plus b is less than 1, then the loss is non-negative. Otherwise, we always put a loss. I will now show a notebook where I had implemented this. Before that, let me see if the previous computation has completed. Okay, Kishan.
The yellow support vectors lie on both the sides, but one side is classification.
Your logic seems correct. I don't know why this is happening. If anyone knows, you can let me know. You typically see the yellow points. So let's say that the above class, the above this hyperplane is the red class, below this is the yellow class. So typically you should see the points, only yellow points over here. I don't know why this yellow point is called a support vector. Does anyone have a clue? I don't know. Perhaps it's just that the optimization is not working well. It's getting confused with such high values. You typically don't give such high values. Like here it doesn't make sense also to do that. And as I was also mentioning, typically you never just solve the problem until unless it's a very simple problem. You never just use the soft margin SVMs. We typically use a combination of kernel SVMs and soft margin SVMs. By default, sklearn has c equal to 1.0. So therefore, if you by default use sklearn's SVM, it is not a hard margin SVM. It is a soft margin SVM, which allows for some slack. So slack, as you've seen, will make the problem better numerically. It's more better condition to be solved. Otherwise, this one is a very poor example. Now I will definitely remove this so that we don't. until unless we are able to figure this out, let's not go into the details of this. Now we had previously seen the loss in the objective in the loss plus penalty form. It's this minimization of the hinge loss plus the regularization term. So I just wanted that to show that you can also implement this in few lines of code now. So I'll write this as a soft margin SVM nn dot module. Why am I using nn dot linear here? So remember what do you do in SVM? So you do Wx plus B, which is equivalent to nn dot linear, weights and biases. So this is a neat implementation. Here I am hard coding it to 2, but you could also, while the time of initialization or calling the fit function, you could get that from the input dimensions. The forward is just self dot linear of x. The hinge loss is torch dot mean of torch dot max of torch dot zeros like y true 1 minus y true into y pred. So this is max of 0, and then the second term is 1 minus yi, and this thing we can also just call yi hat. This is just the prediction from the linear model yi hat. So therefore 1 minus y true into y pred. The way we get the y pred is we call the forward method. So in the training I'll show you y pred is model of x input, and then my loss is model dot total loss of y torch and y pred. So my losses are two losses. The first one is the hinge loss, max of 0 comma 1 minus y true into y pred, why y pred is this quantity wxi plus b, and I can also equivalently just remove this and write it this way. So you get min of summation I equal to 1 to n. Here we are not using summation, we are just using the mean. We could have also used just the torch dot sum, and the regularization loss is 1 over 2 c and the magnitude of w squared. So self dot linear dot weight gives you the w and w vector, and similarly you can get the b coefficient also and half of that, and then the total loss is the sum of these two losses. I am using the same data, I have just kept C to be 1.0. Again, importantly, I have to convert from the 0 class to the -1. So wherever I have y is 0, I have to keep it to -1. One simple function that I am using to get that is 2 into y minus 1. If y is plus 1, I get 2 into 1 minus 1, which is 1. If y is 0, I get 2 into 0 minus 1, which is minus 1. So it's a neat, convenient way instead of having to use lookup where y. So I could have also done this using y of y equal to 0, set it to be -1. I keep 1000 epochs. I can just convert this to atom. And if I now train this, I get my final loss is 0.516. I can also get the w vector and the b value. I just use model.linear.weight and model.linear.bias to get me 0.2 and minus 0.4 and 0.7. I can then plot the margin as we've been doing earlier, so nothing new in that. And if I plot that margin, it looks something like this. Now instead, if I directly use sklearn's function, SVM and the linear kernel with c equal to 1, and if I get the values of w's and b's, they are not exactly similar. So I am getting 0.2 and minus 0.4 and intercept of 0.78, whereas they are getting 0.1 and minus 0.9 and 2.4. Does anyone know why we are not getting the same values of w's and b's? And if I am to look at the plot also, you can see that in sklearn the margins are narrower compared to my implementation of torch. Does anyone have any clues as to why this is happening? Did our formulation look okay? So it looks okay to me. but I was not able to get the exact same results as SVM from sklearn is having. So my guess is that they are using some slightly different form of the loss function, and they're also using different solvers. So both of these can create an impact, but potentially they're also maybe normalizing the data x, they're also varying. Instead of the raw x that I'm using, maybe they're normalizing it. So bunch of these factors could be playing here. I think it will be good exercise for you if you can find the time for this to get the exact same results from both the implementations. So then what I also tried to do was to compute the loss given the set of parameters learned by my torch implementation. That gives me 0.51, and the loss which sklearn's SVM returns, that is much higher. So perhaps this loss is also incorporating some of the terms, I don't know, or some other function of the terms that we have. So it will be good exercise to look at it. You could also perhaps just go into the score function and then look exactly what they're doing here, or I would actually maybe just go into this function, this implementation. They say that they are internally using libSVM, or it's based on libSVM. I would go and search here or in some other places what the exact loss function that they're using, and maybe from there we will be able to figure out and use the same one in our implementation, and we should then be getting exact results. So this is just a good exercise for you to learn what SVM is doing in sklearn. I tried a bunch of other things, like including setting the same weights as SVM's model, and so here I did this. If my torch implementation's weight and bias, I set that to be the implementations, the SVM's coefficient and intercept, and then I plot the boundaries. They will naturally be the same because the boundaries are w dot x plus b equal to 0. So that's it for the SVM part of the lecture. Now many of you might be wondering why we are discussing SVMs at such extended lengths. Maybe we didn't give this much time to the other topics. Does anyone know why? There are a few reasons that I had. Why should we be studying SVMs in such extended duration, for such extended duration? These are non-technical questions, so at least now you can respond. So one, it introduces you to the concept of kernels. Kernels are not restricted only to SVMs. You can also, for example, see kernel ridge regression. sklearn has this. So you have something known as kernel ridge regression. You can in fact also write ridge regression in the dual form, and then you can kernelize it. So whenever you write something in the dual form, it's very natural to kernelize it. You also see kernels extend a lot in things like Gaussian processes, which are very powerful methods for regression. And you also can then see the relationship between Gaussian processes and neural networks. There are some very neat relationships. If you have a neural network with infinite width, you can equate that to a Gaussian process. And then there are also interesting things like similar to that, neural tangent kernel, which also, so for anyone who's interested in theoretical ML, knowing a little bit about kernels will be highly useful. So there also you are trying to look at the kernel evaluations. We have seen that they are very expensive. Thus far no one has asked a question on that. But kernel evaluation, you are computing all things pairwise, and then in many methods you end up inverting those covariance matrices. That is also expensive. So then there are methods which can look into approximation of the kernel functional evaluations. So as an example, I could, for example, whenever these values are below a certain threshold, I could just set them to exactly 0. So therefore I don't need to compute all of these values. I can just set them to 0, which will reduce the number of computations required, and the inverses also becomes easy. So a lot of applications of kernels, not just in regression settings, SVMs can also be used for things like regression. Sorry, not just classifier. SVMs can be used for regression. They can be used for anomaly detection. They can also be used for clustering. They can also be used for ranking. So SVM plus ranking is a very powerful combination. And kernels, you can also use kernels for other kind of data. For example, you should think of kernels are trying to encode similarity. How would you encode similarity for categorical variables? Maybe using Hamming distance. Or how would you encode similarity for things which are, let's say we are trying to construct similarity between 2 points on the earth. Would you use Euclidean distance or would you use geodesic distance? Or if you're trying to compute the similarity between 2 strings, maybe you will use the similarity notion as something like the edit distance. Right? So therefore the concept is very general. You can leverage these concepts in a variety of applications. Any final doubts in this lecture? Okay, thank you. Otherwise, we'll meet on Friday.